that. Okay. Are we ready or what? Great. I know this half of the room is ready. How about this half of the room, the chatty half of the room? Now that we have this clear divide. Yeah, this is the best. Fight it out. Fight it out. Okay. So hey. All right, so we started chapter 6, right? Chapter 6 is on annuities. We did. So we started talking about annuities. Do you guys remember what annuities are? Annuities are when we're making regular payments or getting regular payments is the better scenario, right? For some length of time, we're getting payments, right, at regular intervals. So they're just regular payments. Made for a specific term. So think car payments, right? Usually we're not getting money unless you loan someone money and then you're getting money back, right? But car payments, right? Some set amount every month, usually for, let's say, 5, 4, 8 years. I think you can do 8, I don't know. Sounds like a long time, right? But you're making regular payments for some specific amount of time, and then you're done, right? To pay off some amount. Or you're making payments into, say, some sort of savings plan, like an RRSP or whatever, right? You're making regular contributions for some amount of time, and in the end, you'll have some saved amount, right? So we started talking about the different types of annuities, but before we did that, we talked about the effective interest rate, but more importantly, how to change from one compounding frequency to another, right? And so we talked about annuities, of course, and we said we can have ordinary annuities, ordinary, where the payments are at the end of the payment period, right? I'll just say payments at the end, right? Or an annuity due, where payments are at the beginning. We can also have, right? So each of these, we said, can be simple, right? Or general annuities. Yeah.
Is the ordinary one the simple one, or is this 2 other categories?
So this is 2 other categories. That's why my tree looks a little weird. Because under each of these, right, you can have ordinary simple annuities, ordinary general annuities, or annuities due, simple annuities due, or general annuities due. Right. So we're just kind of making our way through this forest. Okay. So a simple annuity is where the payment period and the compounding frequency are the same, right? Then we don't have to make any adjustments, but we kind of foreshadowed and we said, okay, well, usually the payment period and the compounding frequency aren't necessarily the same. And that's when we need to be able to move from one compounding frequency to another to get those to match, right? So this is when the payment frequency equals the compounding frequency. Whereas a general annuity is where, of course, the payment frequency is not equal to the compounding frequency. So we outlined these last thing, but in the case of general annuities, right, we have to use that I2 formula that we looked at. So in the case of general annuities, we will need to convert the compounding frequency to match the payment frequency. Using the formula that we developed last day, I sub 2, right, that's your new periodic interest rate, is 1 plus I1, your previous periodic interest rate, to the power of F1 over F2, all minus 1. Right, where I1 is the original periodic interest rate, F1 is the compounding frequency, and F2, we're going to move towards making that the payment frequency, right? Because we want our new compounding frequency. So it's the new compounding frequency, which we need to make the same, which is equal to the payment frequency. Because that's the whole goal of it all, right? We can't change the payment frequency because that would be weird, right? And so we change the compounding frequency because we have that formula to match the payment frequency. And then we can just use that I2 as our I. So we talked about ordinary simple annuities last day. Today we're going to get to ordinary general annuities. The naming kind of throws me off because then it's annuities, simple annuities do different order. Doesn't matter. Okay. So we said, so we have the formula on our formula sheet. Oh, so annoying. But that's how I know the sound's recording, so I guess it's good. Can't fix it though. We have the PMT. All right, this is just on your formula sheet, and we talked about it last day. Big brackets, little brackets, 1 plus I to the power of n minus 1 over I, right? Where n is the number of payments. That was confusing for a little bit, right? Because n used to be the number of compoundings, right? But now n is the number of payments. But remember, we have to adjust our compounding frequency to be the same as the number of periods, or the number of payments. And so they're the same, right? Once we make that adjustment, it would be the same, right? But n is going to be the number of payments for annuities. And we talked about the present value formula. Notice the difference between what we're used to seeing, right, for compound interest that we were dealing with. We had the future value and the present value in the same formula, and we could kind of move between the two. right? For annuities, we have two separate formulas for future value and present value, right? So it's going to depend on which one we need. That's the one we're going to pick, right? Same thing for calculating N, which we'll do today, right? That's going to depend on if we know the future value or if we know the present value. Right? So we have the present value formula is the PMT times 1 minus 1 plus I to the negative N all over I. And we did examples doing this, right? The changes for our timelines, right? How we draw our timelines is going to be a little bit different, right? Because now we have all these regular payments, but remember we just do the beginning point, the end point, and then 2 at the beginning, 2 extra at the beginning, and 1 extra at the end, and then dot, dot, dot in between, right? And then we funnel them in to one future value or present value. But we'll do an example again. Okay, so any questions about that before we get into 6.3? No. 6.3, calculating the periodic payment it's your PMT, right? And number of payments. N. So there's no formula for PMT, right, on here, but we do have PMT in the future value and the present value formulas, right? So if we know whether we know the future value or the present value, we can use those to solve for PMT in either case, right? So solving for PMT. Okay. So if we know the future value, right? It's a comma. Plug in all the given values into the future value formula. Oops. Into the future value is the PMT times 1 plus I to the power of N minus 1 over I, and then solve for PMT. Which I think you guys would have arrived at anyways. I don't need to tell you to do that, right? But that's just what how you're going to solve these, right? Same thing, yeah. Well, it depends on what you know, right? If you know the future value, then you have to use the future value formula, right? But of course, if you know the present value, right? Or if we know the present value, we use the present value as the PMT times 1 minus 1 plus I to the negative N square bracket over I. And then solve for PMT. Questions back there? No? Okay. So it depends on what you know, right? In either case, you're going to need to know I and you're going to need to know N. Right. So let's do an example. Let's do example 212. Where did I put those little guys? Nope. Oops. Your RRSP goal is $300,000. Okay? So you're going to be presumably putting money away to have some future value of $300,000. Right? The current interest rate for RRSPs is 8% per year, compounded annually. I don't think so, but anyways, and you intend to retire in 30 years. How large should your year-end contributions be? Right, so we're trying to figure out how much do we need to contribute at the end of each year to end up with $300,000 in 30 years. Okay. So we're going to draw our timeline, right? And so we're going to start today, and we know we're going to be making payments for 30 years. Right. And I'm making year-end contributions, okay? And interest is compounded annually, right? These two are the same, right? I'm compounding annually and I'm paying annually, so they're the same, right? So I don't have to make any adjustments. Okay. And so I've got 1 year, 2 years, 1 year, 2 years, ... to 29 years, right? So 2 extra ticks in the front, 1 extra tick in the back, total of 5 ticks, right? For these annuity timelines. And ... in between. I don't know the payment amounts, right? But the payment amounts go underneath the ticks. And so I'll just write PMT because that's what I'm going to be solving for. It's the same situation as when you just put X when we didn't know the amount, right? But now that amount is called PMT, so we may as well use it. And because these payments are made at the end of each year, right? I don't have a payment today, but I do have a payment at 1 year all the way up to 30 years, right? And then instead of drawing all these future value arrows, which is technically what's going on, we can just do a curly bracket, which I like to think of as a funnel. They'll funnel into this one, or if you want to do square brackets or whatever thing you want to say, okay, these all funnel together and they're all going to make some future value. Yeah. Okay. And we know that this future value has to equal 300,000. I like to highlight that I know that this is a future value, right? Anything on this side of an arrow is a future value. Anything on this side of an arrow is a present value. And so now I know, okay, the future value has to be 300,000. Right. So I know the future value, so I have to use the future value formula. Right. First, let's list the interest rate. So R is 0.08 and F is yearly, so 1. I can't leave it alone, even though I is just going to be 0.08. 0.08 divided by 1 is 0.08. I just can't help it. And if we're making yearly payments for 30 years, we've got n equals 30 payments, which I put on the arrow. Cool. So now, right, we have two options for finding our PMT. We don't know the present value, right? Technically, the present value of this is 0, right? You start with nothing, so, and then you're making contributions. So we have to use the future value formula. So the future value formula is the PMT square bracket 1 plus I to the power of n minus 1 over I. Future value, we're told, has to be 300,000. We're trying to solve for this PMT. 1 plus 0.08 to the power of 30 minus 1 over 0.08. We can solve for that, right, as long as we're careful. And in fact, I'm not going to stop in between and show my work because it actually is just easier to just power through. So 1 plus 0.08, just make sure that you get the same thing to the power of 30 minus 1 divided by 0.08. I get PMT times 113.283211 end bracket 111 is 300,000. So just make sure that that's what you get. And then to solve for PMT, PMT is 300,000 divided by 113.2832111. Two, 6, 4, 8.230016. So each payment must be 2,648.23 pennies. Nice. I'm not going to do an example with the present value because it's the exact same, but you can see example, oops, 213, or there's lots of examples for an example with the present value instead. But you do the exact same thing, right? You plug in your values for I and N and your present value instead, and then solve for your payment amount, right? So now we know that payments of $2,648.23, right? That's what would get you to 300,000 in 30 years if you're contributing that annually. Cool. How about solving for N? We have that these big formulas for N, right? Again, depending on if we know the future value or the present value, that'll dictate which one to use. So, solving for the number of payments. N. If we know the future value, we use, oops, N is the log of 1 plus I times the future value over the payment amount, all over the log of 1 plus I. That's on your formula sheet. Right. The future value there. If we know the present value, we use N is the negative log. Don't forget that negative. Is it 1 of 1 minus I times the present value over the PMT. It's slightly different format. Over the log of 1 plus I. Keep jumping around. Yeah. So depending on which one you know, right? Everything else in here is the same. You need to know I and you need to know the payment amount. So let's do example 216. Maxwell borrowed, $20,000 from loan shark Alec. Sounds like a bad deal. Alec demanded year-end payments of $3,500. How long will it take to pay off the borrowed money if Alec charges 17% interest compounded annually? Yikes. Loan shark Alec strikes again. So we're making year-end payments, right? And interest is compounded annually. So these are the same, so we don't have to do anything, right? Today, later on, they won't be the same, so we have to make adjustments for that. Right? Yeah. So he's demanding year-end payments, and we want to know how long is it going to take, right? Which means we first have to figure out how many payments, and then once we know how many payments, then we'll know how long it takes, right? Just the same as before, where we had to solve for the number of compoundings to find time. Okay, so we're going to draw our timeline. It's a little bit trickier because we don't know how long this timeline is, right? But we know that we have to make N payments, right? So, and we're making year-end payments, so that's making it a little bit easier. So we've got today and 1 year, 2 years, up to N minus 1 years and N years, right? Dot, dot, dot. So we're making payments of 3,500, 3,500, 3,500, 3,500. These are all to pay off a loan of $20,000. So a loan that you get is some present value, right? Because these 3,500 are working towards paying off that present value, right? And so these payments they're all going to funnel back to a present value. And that present value is equal to 20,000. But again, I like to show off that I know that, hey, this is a present value. And it's also a reminder, right, that, okay, present value, that's the one I know. So that's the formula that I have to use. Right? So in general, right, if you're paying off a loan, the loan amount is your present value. Right, if you're saving towards something, your total savings at the end, that's your future value. Right. So we also know that the rate, R is 0.17 and F is just 1. I'll do it. Some redundant stuff there. But I'm a sucker for completeness. I is R over F. R is 0.17 over 1, which is 0.17. I did it. Okay. And we're trying to solve for n. Right? So we can just say n question mark. Right? It's the whole goal. Great. So now we have this complete timeline. Right? And if we're looking at our formula for n, right, and we know since we know the present value must be $20,000, we're going to use n is the negative log of 1 minus I times the present value over the payment amount over the log of 1 plus I. What if I asked you this? What's the future value of all this? Technically it's 0, right? Because it's all paid off. Right? So there is a future value, but it's 0. Just like before when we were making payments towards an RRSP, right? The present value was 0 because we're starting at 0. Right? And that's why they're not included in those formulas. Right? So time to plug and chug, I think. We have I, we have the present value, we have the payment amount. Let's do it. So we've got the negative log of 1 minus I, which is 0.17, times the present value, which is 20,000, over the payment amount, which is 3,500. I threw in some extra brackets in there just to emphasize that I'm multiplying I and PV over PMT over the log of 1 plus 0.17. This is where the store functions are going to come in handy, I think. Right. So we're going to start with our 20,000 divided by 3,500 times 0.17. 1 minus that. Oops. You could just go straight through to the end, but I'll just pause in so you can check to make sure that you got that first bracket done. 0.028571429. Did you do 1 minus or minus 1? Yeah. You'll want to be careful that you do 1 minus because it becomes something like 0.9 something. and then do 1 minus that.
Oh yeah,
Be careful. Over the log of 1.17. So now if you take the log of that, it's going to be negative, so we undo it with a negative. Divided by 1.17 log. I get 22.6449883.4. Let me see here. Yes. I'll just redo it here. So 20,000 divided by 3,500 times 0.17. 1 minus that. Oops. Take the log of it. Here, I'll just show this in more detail. Here, it's negative 3.5553486061. May as well store that in one. And then 1.17 log over 0.157003.749. So we would need 22.645 payments. Do you think Loan Shark Alec would be okay with 22 payments? Probably not. I think he's going to want 23 payments. We would need 22.645. Loan Shark Alec would need a full 23 payments. Right. 22 payments, you wouldn't be quite done. So you'd have to go for 23 full payments, right? For N, we always round up, right? Even if we got to 22.01 as our N, you would have to go for a full 23 payments, just because 22 wouldn't quite get you there, right? Cool. So, yeah, make sure you get your logs all sorted out there. But besides that, not too bad. Same idea if you know the future value and you need to find how long it's going to take, right? Here, we're making payments each year, right? Therefore, to answer the question, it would take 23 years. For who was it? William Maxwell. Don't know why I thought similar names. Maxwell has to make payments for 23 years for what seems like then a measly $20,000. Terrible. How much will he have paid to borrow this $20,000? He'll have paid 3,500 times 23. He'll have paid $80,500 to borrow $20,000. That's rough. He will have paid, right, 80,500. $23 times 3,500. It's tough. That's no, I just like to throw that in there for perspective. Yeah, if you just ended at, it would take 23 years. That's all I'm looking for. Yeah, that blows. That's what this whole course is about. Don't borrow money. Yeah. Okay, so from here, now that we've introduced all these concepts about annuities and these regular payments and these formulas that we use, right, going to ordinary general annuities now isn't that big of a stretch, right? The only thing that we do in between is we have to make sure, okay, what's our compounding frequency and what's our payment frequency? If they're not the same, we have to make that adjustment before we start, right? And then we just use the same formulas, right? Same thing in chapter 7. We just make sure, okay, are the payments being made at the end of the payment period or at the beginning, right? If they're made at the beginning, we'll have an annuity due, right? And that's chapter 7 stuff, but all the concepts stay the same. So we just kind of steamroll through chapter 7, even though it's big concepts, right? But we've already talked about them in chapter 6, just making that little tweak where the payments are being made at the beginning instead of at the end. So you kind of already know what the rest of the course is all about, just having done all this, right? So any questions before we start 6.4, ordinary general annuities? Ordinary general annuities. Ordinary means that the payments are at the end. Oops. Payments are at the end. And general means that the payment frequency is not the same as the compounding frequency. So the first thing we need to do, right, is if the payment frequency is not the same as the compounding frequency, right, we need to adjust the compounding frequency. So we will need to adjust the compounding frequency to match the payment frequency. Right. So we have to use I2 is 1 plus I1 to the power of F1 over F2 minus 1. All right. Where I1 is the original periodic interest rate. F1 is the original compounding frequency. And F2 now, that's the compounding frequency we want to move to, right? But it's going to be the same as the payment frequency. Right. It's going to be the new compounding frequency. We could have had this step in the beginning, right, for simple annuities, where F1 is the same as F2 essentially, right? Right, the compounding frequency is the same as the payment frequency, right? But if, so for simple annuities, F1 equals F2, right? That's the definition of a simple annuity. The compounding frequency is the same as the payment frequency, right? So if we had to find I2 in that case, which we could have done, right? Use the same steps, but it would be a little redundant. I'll show you why, because you would have 1 plus I1 to the power of F1 over F2 minus 1, right? Yeah. I swan. Okay. But if F1 is equal to F2, right, then this is the same as 1 plus I1 to the power of 1 minus 1, right? Since F1 is equal to F2, right? One number over itself is just 1. So what do we get then? We get 1 plus I1 minus 1, just I1. Which makes sense if they're the same. But really, we just get I2 for simple annuities. So we could have done this calculation over and over and over again earlier for simple annuities when they were the same, but it would get annoying because we would just get back to the same value, right? So now that F1 is not the same as F2, right? The compounding frequency is not the same as the payment frequency. Now we'll get a different I2, and that's when we start actually doing it. Okay? But I just wanted to show you why we weren't doing it before. So let's do example 218. Suppose month-end payments of 300 are made on a car for 4 years. If the rate of interest is 5% per year, compounded quarterly, oops, highlighted the wrong thing, compounded quarterly, what's the value of the car? So first thing we're gonna do, right, is we're going to say, okay, well, F1 is the compounding frequency, which is 4. And F2 is the payment frequency, which is monthly, so 12. So before we even do our timeline or anything, right, we need to find I2, right, because R1 is 0.05, right, which means I1 is R1 over F1, 0.05 over 4. .0125. F1 is not the same as F2. Need to find I2, right, before we can even get started here. I2 is 1 plus I1 to the power of F1 over F2 minus 1. As long as you remember that F1 is where you're coming from and F2 is the frequency that you want to move to, right? You don't actually have to remember that F1 is the compounding frequency and F2 is the payment frequency. Those will just come naturally, right? Because you want to move from, you can only change the compounding frequency to match the payment frequency, right? So you want to move from F1 to F2. So you have 1 plus 0.0125 to the power of 4 over 12 minus 1. So plus 1 to the power of 4 divided by 12 minus 1. So I2 is 0.00414942.5. I'm going to store this in 1. Because I'm going to use it a lot in those formulas, right?
What order did you put it in your calculator?
1 plus 0.0125 to the power of, and then I put brackets around my 4 over 12. Oh, that'll do, yeah. But yeah, do make sure that you're getting the same values. Otherwise, you'll be hooped. Yeah. So now, right, the equivalent rate compounding monthly instead, right, because we're making monthly payments, is 0.0041494425. Right, so that's the I that we're going to use. So now, use I equal to I2, which is 0.004149425. So once you found your I2, that's your I that you're going to use from now on. Now we can draw our timeline. Right, so what's happening here? Can't remember. So we're making end of the month payments of $300 are made on a car for 4 years. What's the value of the car? Right. So these $300 are paying off this value, the initial value of the car. Right? So that's going to be a present value. So we're gonna draw our timeline. And we're gonna start today. And I'll write 4 years up above here just because we're making monthly payments, right? So each of these ticks are gonna represent months, right? So I've got 1 month, 2 months, 4 years. 4 times 12 has 48 months. So that's why I put the 4 years up above a little bit, just because I know I'd have to make my ticks in terms of my payments, right, where my payments are. So it's just nice to see 48 months instead, because then if I just put the 47 months, instead of 4 years minus 1 month, doesn't really make sense. And then I can do dot, dot, dot in between. So I'm making payments at the end of each month. So at the end of each month, I'm making payments of $300. 300, 300, 300. And these are all to pay off the value of a car today, right? Making it a present value. So this here, value of the car today. How much you bought it for. So we want to know the present value. So we have to use the present value formula. What's the future value? Future value, once the car is all paid off, the future value of the loan is 0. Right? So that's why we don't care about the future value. We want to know how much are we paying off. So we use our present value formula is the payment amount times 1 minus 1 plus I to the negative n. Oh, I forgot to put my n on there. Over I. Here, how many payments am I making? 48. Remember to use your new I2 as your I, right? So that's why we had to store it. I stored it in 1, wherever you stored it is fine. But our PMT is 300 times 1 minus 1 plus 0.004149425 to the negative 48 square bracket over I, which is 0.004149425. Right, up until now, we've been dealing with nice I's, right? So we haven't had to store them as much, but now we definitely want to keep all our decimal places, right? So we want to store all these values as we go. Okay. And yeah, once we get into these bigger ones, I'm just going to plow right through, get that big bracket just sorted out. Okay. So 1 plus recall 1 to the power of 48 negative 1 minus that. I'll show 1 step in between so you can just double check. But in the future, I probably won't. 0.18025363 over 0.004149425. divided by recall 1. $300 times 43.44063287. Times 300. $13,032 and 18986. So the car costs $13,032.19. Cool. Shall we do this on our calculator? Might be handy. Yes, but using the buttons. Oh, really? Well, aren't you in for a treat? So we've used the buttons before, right? But we were leaving the PMT amount as 0, and the payments per year we were just setting to be the same as the compoundings per year. Right now we know what those mean, right? The payments per year is the payment frequency, compoundings per year is the compounding frequency, right? So we already kind of know how to use our calculator to solve this, right? So we can solve this on our calculator using the time value money functions. On the final exam, there's going to be an annuity that you have to do by hand, but then there's also annuities that you can just use the time value money functions if you want to. You're allowed to do it by hand if you want to, but might want to use the functions. So if we're going to use these functions, we list all the entries that we have to fill in, right, with the values that we're going to enter. Right, this is the same as showing all your work in your calculations, right? So N is something, the interest per year, are you guys getting the same values or what? What's going on? What's the discussion over there? It happens. It won't end well, but it happens. Future value, the payments per year and the compoundings per year. So for N is now the number of payments. Number of payments. The interest per year, right, is the nominal rate as a percentage still, right? We have to remind ourselves that, okay, if it's 7%, right, then we just put 7, not 0.07. Right? So this is the nominal rate as a percentage, right? For example, 7%. Use just 7. That's important. PV is the present value. Of course. PMT is the payment amount, just like in the formulas. Right, that regular payment amount. Future value is the future value. payments per year is the payment frequency. And the compoundings per year is, of course, the compounding frequency. Just looking at PV, PMT, and the future value. So we did start to adopt this kind of method, right? So for money leaving our hands, we were going to make a negative, right? And for money coming to us, we use positive values. And the one thing to keep in mind is that the present value and the future value have to have opposite signs, right? But now it's really important because are these payments positive or negative, right? Depends on if you have to make these payments to pay off some loan, right? Or if you're getting these payments, right? If someone's repaying a debt or whatever, right? And so that's why it's going to matter if the payment amount is positive or negative, right? Because is it money in the bank for you, or is it or money to you, or is it money out from you? It's going to make a big difference. So payments leaving you will be negative, and payments to you will be positive. We already used that convention, right? But now it's actually going to be important. The present value and future value must have opposite signs. Right. One has to be positive, one has to be negative. So what if we did this previous example just on our calculator? Because we know the answer. If we're using our calculator, then as long as we know our compounding frequency and our payment frequency, and we enter those, we don't have to solve for I2, right? It'll just do it internally for us. We do have to know our N, right? And our payment amount and our future value and our present value, right? We also have to keep track of if the money is leaving us or coming to us, right? And so we can redo example 218 on our calculator. Right. Timeline would be the same. Let's just enter the values that we have. And the interest per year, the present value, the PMT, the future value, the payments per year, and the compoundings per year. So we said we have 48 payments. The interest per year, so the original interest per year, 5. Nice. And while I'm at it, I'm going to put in the payments per year and the compoundings per year, right? Because I think we're making payments 12 times per year and compounding 4 times per year, right? The payments are 300. Are they leaving me, or I think I have to pay off a loan, right? And so, right, minus 300. I'm paying off a loan. My present value, that's what I'm trying to solve for, right? And so what we do, right, is we put a little star here to indicate that, hey, this is the one I'm solving for. And then when we've solved it, then we can put it in. But temporarily we put 0, right, in our calculator. And then we can put our value into that slot later. Okay. Solving for this. The future value has to be 0, right? We said, okay, at the end of all this, I'll be done paying off this loan. And so the total owing at the end has to be 0, right? And I'll just make it -0 just because then I'll get a positive present value, right? Which is right because I got some loan amount, right? And so when I get a loan, right, that's money to me, so it's going to be positive. Right? So here, right, loan is paid off in the future value, so it must be 0. Okay. So, do you guys remember entering all this stuff? We just fill in the slots. So 48n, and then as long as it says n equals 48, it's logged. You can just keep moving on. In fact, you can't really check what it thinks it is, right? So it'll just keep overwriting. So n equals 48, it's locked in. 5, interest per year. 0, present value, right, until we come back to solve for it. 300 negative, that's a new one for our PMT, right, but it works the same. And then 0 negative for our future value. I don't think it lets me do 0 negative. 0, 0, doesn't matter. And then if you go into your second menu, the payments per year is over the interest per year. So second, payments per year, we have to change that to 12, right? If you're in a second menu, you have to hit enter to store it, right? You want to make sure that it says payments per year equals 12, right? And then scroll down using the down arrow and change the compoundings per year to 4, enter. And then you can scroll up to make sure the payments per year is still 12, compoundings per year is still 4, great. And then you can second quit to get out of there. So now we've filled in all these slots, right? And so you're going to compute the present value. So CPT, compute present value. Well, what do you know? $13,032.18986. Sound familiar or what? Blank or like 0. Did you hit second quit? Okay, then hit CPT PV. Yeah. Equals. Did you get it?
I had to actually push CP for it. Like when I compute, nothing happens. Then I have to do that.
Yeah, you have to tell it what to compute. Yeah. Nice. Cool. So that's a little nicer, hey, than having to solve for I2, solving for the present value, but you do end up at the same value, right? All right. Questions about that one? Then let's do another example. Example 219. $219. All right. So, Tom and Delilah wish to start a college fund for their daughter. Their goal is to put $200 into the account at the end of each 2-week period, right? So bi-weekly. Okay. Assuming that college fund will earn a rate of interest of 3.75% compounded quarterly, how much will be in the account in 20 years? So we're going to start by figuring out what our compounding frequency is and what our payment frequency is, right? So we start by saying, okay, F1 is our compounding frequency, which is quarterly, so 4. F2 is our payment frequency, which is our bi-weekly, 26. Right, every 2 weeks. We know that R1 is 0.0375. So I1 must be, R1 over F1, which is 0.0375 over 4. 0.0375 divided by 4, 0.009, 375. That's your original periodic payment, interest rate, sorry. So now we have to find I2 before we can even start anything, right? I2 is 1 plus I1 to the power of F1 over F2 minus 1. 1 plus 0.009375 to the power of 4 over 26 minus 1. Plus 1 to the power of 4 divided by 26 minus 1. I get an I2 of 0.00143662, which I'll store in 1. So this is the I that I'm gonna be using for all my calculations. So we'll first do it by hand and then we'll do it on our calculator. They'll be the same, which is kind of rewarding. It's nice. So regardless of how we do it, we have to make a timeline. So we start today, they're making payments for 20 years. But same scenario as before, right? I'm going to put the 20 years a little bit above, making room for, because we're making payments bi-weekly, right? So all these ticks are going to be bi-weekly ticks. And so here we're at 2 weeks. Then another 2 weeks goes by, putting us at 4 weeks. 20 years. 20 years is, I'll do it in weeks. So 20 times 52 weeks is 1040 weeks. So 2 weeks before that is 1038 weeks. If you instead wanted to do 1 biweekly, 2 biweekly, 520 biweekly, 519 biweekly, that would be okay, but it doesn't really, I don't know. I don't think in biweeklies, so something tells me you don't either. Even if it is biweekly, we work in weeks, right? So, and they're making $200 contributions. Okay. So $200 here, $200 here, $200 here, $200 here. And these are all going to funnel into some future value, right? Because they're making these contributions to save up for some future amount, right? How many payments are they making? Nice. $520 payments. And it's still time times the frequency, right? It's just times the payment frequency, right? N is time times F2, where time is in years. Oh, 20 years, sorry, not 40. Times F2, which is 26. Right. So N is still time times the frequency, but now the frequency that we're talking about is the payment frequency, right? But the formula is the same. Just so it doesn't feel like I'm pulling these number of payments out of thin air. Okay, so, so we want to find this future value, right? How much will they have in 20 years? So we want to find the future value, so we better use the future value formula. Future value is the payment amount times 1 plus I to the power of n minus 1 over I. The payment amount is 200 times 1 plus 0.00143662 to the power of n, which is 520, all minus 1 over 0.00143662. Good thing we stored that. 1 plus recall 1 to the power of 520 minus 1 divided by recall 1. I get 200 times 772.38011011. Times 200. I get 154,476.0202. they would have saved, oops, 1,000 or 154,476 and 2 pennies. Nice. How about on our calculator? Example 219 on our calculator. Timeline stays the same, right? You still have to do a timeline even if you're using the time value money functions. Just the calculations go in these little slots. So we have to say what we're filling all our slots with, whoops. And the interest per year, the present value, the payment amount, the future value, the payments per year, and the compoundings per year. And we had to find on our timeline, it's 520. The interest per year was 3.75. Right? Remember, you want the nominal interest rate. The present value has to be 0. Right. I'll make it negative just so that my future value can be positive, right? Because it doesn't matter, right? It won't let you make the 0 negative anyways, but on here, I'll make it negative. And my payments, so their payments are leaving their hands, right? $200 each month or each bi-weekly period, right? It's leaving their hands. So we have to make it negative 200. I'm solving for this future value. So I put a star there and then I can fill in that slot later. We temporarily fill it with 0 and then we go back and compute it. The payments per year are 26 payments per year and the compoundings per year is 4. So here we go. 520N, 3.75 interest per year. 0, I'll try negative, present value won't do it. 200 negative payment amount. 0 for the future value. Payments per year are 26, enter, and the compoundings per year are 4, enter. Second quit, compute future value. We get 154. It's a thrill, isn't it? 476.0202. Feels good. And I'll just highlight that they're the same. Let's do example 220. Just on our calculator. Things got weird with this bendy page. Oh well. We'll cross this out. Use time value money functions to solve. So we're still going to make a timeline, right? But we're just going to use the calculator functions to solve it. So Brad has 25,000 saved in his RRSP. It pays 6.8% compounded quarterly, and Brad will continue making month-end contributions of $400 until he reaches a savings goal of $450,000. How long will this take? Right. So we need to find out first how many payments he has to make that happen, right? And then we can figure out how long it's going to take. So first need to solve for n before we can solve for t. Sound familiar? Should. Okay. So let's draw out the situation here. It's a little bit different from what we've seen. Oops. So we're going to start today. And for some, I'll start by putting just a question mark there because we're trying to figure out how long is this going to take. Right. And I think we're still, I could tell. Okay. That was weird. I think this one's supposed to be on mute. Anyways, this one's not on mute. I'm just gonna roll with it. Hopefully it doesn't glitch out even more. We're so close. This is our last example. Okay, so we've got these unknown payments, right? But he is going to make month-end contributions. So all we can say is that here at 1 month, he's making a payment, and then he's making a payment at 2 months. And then here, he's going to go to n months and n minus 1 months, right? We don't know how long, but because the payments are happening monthly, right, we have to go for some n number of payments and months. And he's going to make payments of $400. So each of these payments is $400. So these guys are all going to funnel. Oops. It's giving me that real life pen running out experience. These payments, they're all going to funnel to some future value, right? He'll have saved some future value 1. But we're also told that he already has 25,000 in there already, right? So today, he's going to have 25,000 in there already. So it's going to sit there and make some future value too. And he's going to make payments until the total here is $450,000. So the total, we're forcing it to be $450,000. So it's kind of similar to what we were seeing with our compound interest problems, right? It's just that we've got these multiple payments going on, right? But the idea stays the same. Okay. So now, right, we're just going to use our calculator, and we need to figure out what n is. That's going to be really hard to do by hand, right? So for these types of problems, you have to use your calculator, right? Because how are you going to know what the future values are if you're trying to solve for n? Yeah, they'd have to be the same n, but you don't have payments for the 25,000. It's just sitting there, right? So things are kind of discombobulated. So we have to use our calculator for, you don't have to, it's possible to solve it by hand, but I don't expect you to, right? I expect you to just use your calculator to solve these. How's it gonna look? To show our work, we say n, interest per year, present value, PMT, future value, payments per year, and compoundings per year. We're trying to solve for n. And we're told that across the board, interest is 6.8% compounded quarterly. All right, so I'm just going to put that in here. Interest per year is 6.8, and the compoundings per year is 4. Payments per year, we can sneak that in there, is 12, right? Because we're making payments, month-end contributions, right? So monthly contributions. And so the present value, how you're going to think of it is that he has this 25,000 that he deposits as a lump sum as the present value, right? So we're starting with this, and that's what makes it negative 25,000. So pretend that he had it, and then he just goes and deposits this lump sum, 25,000. And then on top of that, he's adding payments of 400. And at the end of it all, we need a future value of 450,000. So this is how you're going to set these up, right? Where there's some initial amount, right? And then you're adding on payments on top of it to have some end goal savings amount. Or if you wanted to solve for the end goal, the future value, that works too. So for 0, we put in n temporarily, and then 6.8 interest per year, 25,000 negative for the present value, 400 negative for the payment amount, 450,000 positive for the future value, right? Because at the end, he'll get all the amount that he's saved. We're pretending he's just gonna withdraw it and take it home. And then your payments per year are 12, enter. Compoundings per year is 4, enter. Compute n. I get 301.0327. 27127. Same idea though, right? Or he, I guess. Doesn't matter. That's right. He would need to make n equal to 302 payments. right? Same, N is time times the frequency, right? Where F is the payment frequency. Because N is the number of payments. So 302 is time times the payment frequency, which is 12. So how long is it going to take? It's going to take 302 divided by 12. Time must be 25.16 repeating years. It would take approximately 25.17 years. Okay. So that's the end of chapter 6. And over the weekend, I'm not going to assign anything right now, but I do want you to try 6.7, which is that self-test. Pay attention to number 4. It's a gender fluid Albert. Yeah. So do 6.7 self-tests for practice. Okay. Well, I'll see you guys on Monday, I guess.